Hello, I'm Hyung from KAIST in Korea. I will present my work, Teach AI How to Code, using large language models as teachable agents for programming education. It is well known that interactive learning is more effective than passive learning. Interactive learning activities such as discussions and peer feedback can help learners find gaps in their knowledge and construct new knowledge. Learning by teaching is one of the interactive learning activities. In learning by teaching, learners tutor a peer learner, exchange questions to articulate their existing knowledge, and engage in reflective knowledge building. Learning by teaching is not limited to human peers. Learners can also benefit from teaching a virtual agent. In this context, we call the virtual agent a teachable agent. Teachable agents are agents that simulate the role of cuties. Teachable agents facilitate learning by teaching by exhibiting a low level of knowledge and learning from students' explanations and demonstrations. There are two types of pedagogical interactions. The first type is knowledge telling, in which learners tell what they already know with little elaboration. Although knowledge telling can help reorganize one's knowledge, it leads to weak learning effects because the learners do not construct new knowledge. The second type is knowledge building, in which learners elaborate their existing knowledge through questions and discussions. Knowledge telling leads to a stronger integration of knowledge, and is what makes interactive learning unique and valuable. In this work, we explored whether we can use large language models as teachable agents to facilitate knowledge building at scale. While previous non-LLM teachable agents are limited to predefined interaction methods, we thought LLM's high and flexible interactivity can stimulate active question exchange and discussions for knowledge building. Furthermore, LLMs can offload the manual effort and barriers to program teachable agents, making learning by teaching more accessible to a larger population of learners. As a first step, we ran a formative study to look into the potential of using LLMs as teachable agents. We recruited 15 Python learners and asked them to teach binary search to GPT-4. We gave GPT-4 a name, the role it should play throughout conversations, and instructions on its tone and behavior to simulate a tutor. We also gave specific learning challenges on binary search it should exhibit. We found that GPT-4 as is can facilitate learning by teaching, but conversations were limited to knowledge telling, and learners need extra guidance for effective learning. First, GPT-4 was too competent to simulate a tutor. Although we specified the roles and learning challenges in the prompt, after a few checks, GPT-4 self-corrected its misconceptions without being taught. Since GPT-4 learned too fast without help, participants did not have enough chances to learn by teaching it. Second, GPT-4 rarely asks questions that can elicit knowledge building. Participants perceived self-explaining knowledge useful, but remarked that they could not learn new knowledge from the activity. Lastly, LLMs did not give feedback or guidance on participants' teaching methods. Participants wanted to see better methods for them to teach teachable agents and review their learning process. Based on these observations, we set 3 design goals for making LLM-based teachable agents more engaging and pedagogical. First, we need a stronger technical constraint on the knowledge level of LLM-based teachable agents to simulate misconceptions and gradual learning curves. Second, we need to make agents ask elaboration questions to elicit knowledge building from learners. Third, we need to provide feedback on learners' teaching methods to help them reflect and follow good practices of learning by teaching. Following the design goals, we built TeachYou, a learning environment where students can learn introductory programming by teaching an LLM-based teachable agent named Algobo. In TeachYou, learners first solve algorithmic problems and then review the problems by teaching Algobo how to write code for the problems. After helping Algobo solve problems, learners can extend their knowledge through discussions with Algobo. This is the main interface where the learners teach Algobo. The left side has brief instructions about learning by teaching activity, learning objectives, the profile of Algobo, and the problem to teach. At the center, TeachYou provides a chat interface where learners can converse with Algobo. Learners can use free-form natural language to explain concepts and code to Algobo, and learners can also ask questions to Algobo to check its understanding and prompt thinking. Algobo shares its code and asks questions about algorithms, code, and learns explanations. Throughout the conversation, TeachYou analyzes the conversation in real time and gives meta-cognitive feedback and advice on learners' teaching methods. On the right side, TeachYou also provides tools to help learners conduct teaching. Learners can revisit their previous code, use a code playground, and run test cases on Algobo's code. At the backend of TeachYou, we have 3 novel components specifically designed to support each design goal. The first component is the reflect-respond pipeline to simulate misconceptions and gradual learning of Algobo. We wanted to track the changes in Algobo's knowledge through our conversation to control and slow down its knowledge acquisition. However, existing LLMs do not provide a human understandable way to track them. Hence, in this pipeline, we created a concept of knowledge state to represent the knowledge level of LLM-based teachable agents. A knowledge state is a JSON file that stores what Algobo knows. Throughout a conversation with learners, Algobo updates the knowledge state and retrieves information from the knowledge state to generate responses. We developed an LLM-based pipeline for processing the knowledge state. The pipeline has 2 processes, reflect and respond, which are sequences of LLM prompts to add useful knowledge to the knowledge state and to generate responses based on retrieval. The second component is mode shifting, which aims to elicit learners' knowledge building through elaboration questions. We made Algobo switch between a help receiver mode and a questioner mode in every 3 message turns. When Algobo is in the help receiver mode, Algobo passively accepts knowledge from learners and updates its knowledge state. When Algobo is in the questioner mode, Algobo actively asks why and how questions. Learners engage in a constructive loop in which Algobo keeps asking elaboration questions until learners give satisfactory answers. The last component is Teaching Helper, which provides metacognitive feedback on teaching methods. Teaching Helper analyzes the conversation in real time and detects conversational patterns ineffective to learning by teaching. For each detected conversational pattern, Teaching Helper provides adequate feedback in either a red or green box in the chat interface. We evaluate the efficacy of TeachYou on the 3 design goals through 2 studies. For the reflect-respond pipeline, we ran a technical evaluation in which we checked the behavior of the pipeline in simulated settings. For mode shifting and Teaching Helper, we ran a between-subject study to check the comparative efficacy of the components. We evaluated if the reflect-respond pipeline follows 3 desirable properties: reconfigurability, persistence, and adaptability. Reconfigurability refers to how precisely we can set Algobo's problem-solving performance using the knowledge state. To measure reconfigurability, we configured 4 versions of Algobo with different knowledge states and asked 9 multiple-choice questions on algorithms. And we observed how the performance changes across different knowledge states. The second property is persistence, which refers to how Algobo's knowledge level is maintained consistently until it receives useful knowledge. To measure persistence, we ran another experiment where Algobo had a random chat between pre and post tests. The content of the random chat is irrelevant to the tests, so Algobo should show equal performance on the tests if it is persistent. The last property is adaptability. It refers to how well Algobo updates its knowledge as it acquires new information from tutors. To measure adaptability, we use the pre and post test format again, but with correct and incorrect tutoring in between. This time, we gave Algobo information relevant to multiple choice questions and observed how correct and incorrect information affects performance. We measure reconfigurability, persistence, and adaptability with the following setup. We used a static GPT model with the temperature set to 0. We prepared experimental materials for 3 different algorithm topics and aspects of performance. To reduce the randomness inherent in GPT, we repeated the entire experiment 5 times and took the most frequent response. For reconfigurability, we compared 4 knowledge states different in the amount and type of information. We observed that Algobo's problem-solving performance increases with more information in knowledge states. For persistence, performance changed at most by 1. The performance on implementation and analysis questions was kept consistent, but we observed a subtle change in the understanding questions. For adaptability, we found that correct tutoring improved performance more effectively than incorrect tutoring. This result is especially promising in the context of learning by teaching because it will encourage learners to give correct instructions. To check the efficacy of mode shifting and Teaching Helper, we ran a user study with 40 programming learners. We had 2 conditions where the baseline was TeachYou without mode shifting and Teaching Helper. Participants studied binary search and solved a relevant problem. Then, they taught Algobo about binary search and the problem. After Algobo solved the problem, participants were free to spend time with Algobo for discussions. The participants were programming learners who could understand basic Python programs, and we excluded those with high prior knowledge to avoid the ceiling effect. Our key measures were the density of knowledge-building messages in conversations and metacognition. For the knowledge-building density, the two authors classified messages and counted the proportion of knowledge-building messages. For the self-perceived metacognition, we used a questionnaire from King et al.'s study. We found that mode shifting and teaching helper help participants build more knowledge when teaching problem-solving to Algobo. Through a conversation analysis, we found that Algobo and participants tended to prompt each other to expand knowledge more frequently when mode shifting was present. For self-perceived metacognition, we could not observe a significant difference between the conditions. Nevertheless, some participants remarked teaching helper raised awareness about the learning context and stimulated their metacognitive thinking on teaching. We also had interesting observations. First, we observed some tensions between guidance and autonomy. For example, TeachYou tried to control conversation flows for effective knowledge building, but it prevented participants from taking the full authority over the conversation and their teaching methods. To resolve the tension, we may parameterize the balance between the two and change the degree of guidance and autonomy over time. Participants also commented on the difficulty of understanding Algobo's state. Since participants were unaware of Algobo's knowledge state and mode, participants often struggled to give the most effective instructions. Although we hid the knowledge state and the state of mode shifting to reduce complexity, revealing them can possibly make learning by teaching activities more straightforward and effective. Our work opened the possibility of using large language models for teachable agents and proposed design considerations for making effective LLM-based teachable agents. I think LLM-based teachable agents are an interesting example of human-AI interaction, where we do not just want highly performant AI, but need precise control of its performance for desired interactions and interventions. We propose 3 directions for future work. First, future work can look into an advanced LLM pipeline to enable more precise control. Second, we are working on deploying TeachYou to real classes and seeking collaboration with instructors to better support AI-assisted interactive learning in classrooms. Lastly, we can empower educators and learners to build their own teachable agents with natural language prompting. We envision a future learning by teaching system where educators and learners can choose the knowledge level of teachable agents and the frequency of mode shifting for their needs. For more detailed information of TeachYou, please check our paper. Thank you.